Namaste.
How are you,
What do
sir?
you do? Chanagidira?
Yes, sir. ಚೆನ್ನಾಗಿದ್ದೀನಿ, sir. Thank you very
Very
much.
nice, very nice. So we a few more minutes before
Yes, sir.
Okay, good.
Sir, before starting the session, can you please mention the names of the Nobel laureates in the chemistry today announced?
Yeah.
Yes, sir.
Strangely, the names were leaked out this time,
Yes, sir. Yes.
which is a very strange thing to happen for Nobel Prizes. They keep it such a guarded secret till the last moment. So, uh,
Yes, sir. I was wondering till the official announcement from their website itself.
yeah,
So,
yeah, yeah. I'm happy for another reason. It's 3-4 years ago we started working on quantum dots,
yes, sir. Yes, sir. Yes.
but not from quantum dot perspective, but to put them in liquid crystals and bring out anisotropic emission,
Yes, sir.
which is like the polarization of the emission can be controlled using liquid crystals.
Yes,
So
sir.
that's some work that one of my students did 3-4 years ago. So
Okay.
that's why I'm glad to see that this topic got the Nobel Prize.
Sir, what about that display project, sir?
Pardon?
That display by using the groundnut shells.
Okay. We are in dialogue with a company.
Okay.
This is based in Bangalore.
Okay.
They actually work in a very unique kind of area. This is to create fodder.
Okay, sir.
Fodder is a pretty serious problem, especially in some North Indian states, rain-affected states like Rajasthan, for example, Rajasthan and parts of Gujarat. So therefore, more than the food crops which can move around easily all over India because of the kind of infrastructure that we have now, fodder doesn't move so much. So
Okay,
the
sir.
cattle suffer a lot because of this. So therefore, they are creating kind of greenhouses to grow fodder.
Fine, sir.
And this company is developing this in a very big way, and they want good temperature control, and that's where actually we may pitch in to control the amount of light that comes into the enclosure, and also the temperature of the room. So that's where we may play a bit of role.
Great to hear, sir. Great to hear, sir.
Yeah,
All
and
the
but one always keeps the fingers crossed. You
yes,
don't you
sir.
don't know how things go.
Sir,
It's a
and one
small
more thing that
company. It's a bit of a startup actually. So let's see.
okay, sir. And one more thing about that LED plasma display you were working, no, sir?
Not a plasma display. I never worked on plasma displays, not LEDs. But this quantum dot itself, we are proposing that right now quantum dots are used for display purposes. It's
Yes,
already
sir.
in the
Yes,
commercial market, but
yes,
as
sir.
a backlight.
Okay, sir.
So actually, the display is by liquid crystals, but the backlighting, which used to be compact fluorescent light or even LEDs, they are
Yes.
being replaced by quantum dots now because of the high brightness that you can get from quantum dots. So
Okay.
we are seeing that at least we have now applied for a patent. We have a couple of publications on that, etc., wherein we are saying that you can combine the two and make liquid crystal an emissive display. Liquid
Oh,
crystal
great,
that
sir.
has been a bane, that it's a passive display, it needs a light source for it to work.
Yes, sir.
But if we can combine the two, so we have this quantum dot put in liquid crystals, and so we can get anisotropic emission, and so that would avoid one Polaroid. So the light throughput of the device will also be much higher. So that's what our claim is. Let's see.
Anyways, best wishes to all your
Oh,
teachers.
thank you so much. Thank you. Kind of.
So we'll start the session today.
Yeah.
Thank you very much, sir, for accepting our invitation to deliver today's session in this talent search program webinar series. On behalf of KSTA and on behalf of all the teaching faculty and student fraternity, and my own behalf, hearty welcome, sir.
Thank you.
And also, I would like to welcome my colleagues, technical team, non-technical team, and students from various districts who have joined with us in this WebEx platform, as well as who are watching us in the YouTube channel. Welcome to all of you. Before starting today's session, I would like to give a brief introduction about Dr. S. Krishna Prasad, sir. Professor S. Krishna Prasad, sir, is a distinguished scientist working in Center for Nano and Soft Matter Sciences, which is located in Bangalore. And he has obtained his PhD from Raman Research Institute, Bangalore. And his research positions were as a distinguished scientist currently in Center for Nano and Soft Matter Sciences, Bangalore, and retired as a scientist G from Center for Nano and Soft Matter Sciences, and worked as a scientist the Center for Nano and Soft Matter Sciences, Bangalore again, and postdoctoral fellow from University of Florida Naval Research Laboratory, Washington DC, and worked as a scientist in RRI Bangalore again, and visiting scientist Technical University of Berlin, Germany, and a postdoctoral fellow from RRI Bangalore. And his visiting positions held were from Technical University of Berlin, Germany, Naval Research Laboratory, Washington DC, Hungarian Academy of Sciences, Budapest, Bulgarian Academy of Sciences, Sofia, and National Institute of Material and Chemical Research, Tsukuba from Japan, and National Institute of Advanced Industrial Science and Technology, Tsukuba, Japan again, and IT Research Manager in the Japan. And his professional recognition as a fellow of the Karnataka Science and Technology Academy, and member of the New York Academy of Sciences, founder secretary of Indian Liquid Crystal Society and Japan Society for Promotion of Science Fellowship, C.V. Raman Young Scientist Award, G. Raja Raman Lecture in Physics, and member Program Advisory Committee SCRB till 2020, associate editor in the Bulletin of Material Sciences, and referee for several project proposals submitted to serve, and reviewer for several journals of repute, and external expert evaluation of seed funding of research proposals at different institutions, DAC committee member as external expert for PhD students, and current research interests are nanostructures in soft matter, photo-driven effects, absorptive or emissive color in soft systems, organic molecules and fluids, and geometric confinement and energy harvesting from everyday actions. His research outputs are H index 46 and I index 216 with a total citation of 8006. He has granted patents, 10 granted patents and for 5 patents, edited journals issues 2 and book chapters 8, and his research articles in reviewed international journals, more than 300 journals, a PhD guideship, mentorship of research associates, and visiting students of several students. With this brief introduction, I welcome you once again, sir. Thank you. Over to you, sir. And thank you once again for accepting our invitation to be a resource expert for this, to delivering on periodic tables. Sir. Thank you very much, sir. Over to you, sir.
Thank you, Dr. Umesh. Sorry. It has been a pleasure to get associated with KSTA. So I'm really grateful that you gave me an opportunity to give this talk, and I'm thankful to Dr. Sidegowda as well as Dr. Umesh for this opportunity. To speak about periodic table is not an easy job, because the kind of thing that coverage that you need to give is very vast, probably as big as the scientific world itself. So therefore, I don't venture to do that. But rather, I chose a very specific topic. I'm sharing the presentation so that, okay. So kindly confirm that my slide is being seen.
Yes, sir. Yes, sir.
Okay. So probably you would be surprised the kind of title that I have given, at least the first part of the title, Lead Kindly Light. And I have put an asterisk. I will come to the explanation. The second part of the title after the colon is the spectroscopy and the periodic table. It is the first part that probably some celebration should be happening elsewhere in the world today. And of course, being part of the scientific community, all of us enjoy when a particular field gets the recognition by the Nobel Committee, especially. And today I see that Professor Bawendi, Professor Brass, and Professor Ekimov, they have won the Chemistry Nobel Prize, and they have got the prize for the discovery of the quantum dots. And it's interesting to see that even the physics prize went to people who worked on spectroscopic aspects and atosecond lights, extremely small time component wherein the light can exist as a pulse. So spectroscopy is being celebrated in big ways through both these Nobel Prizes. So that's why I'm a little bit elated today that the topic that I chose has something to do with the Nobel Prizes of this year as well. So with that, I want to you to appreciate two images that I have put here on this particular slide, which actually the two numbers seen at the two extremes, 1869 and 2019, talk about the year or the birth of the periodic table, 1869, and the 150 years of that, which was celebrated as the International Year of the Periodic Table. So we are a little beyond the 150 years of the periodic table, and during these 150 years, this very inner-cast looking table, very simple looking table, has captured the imagination of very specifically the material scientists, and a whole series of materials have come about because of our current understanding of the periodic table itself, or the way that chemical elements organize themselves into providing the kind of interesting properties that either they already exhibit or we've coaxed them to exhibit. So with that kind of a thing, I want you to concentrate on the two images that I have put on this. And for making it easier, I am going to zoom it up. So what you see on the left is the way that the master of the periodic table, Professor Mendeleev, Dmitry Mendeleev, he had come up with his table. So this is his lab note or copy of his lab notebook. And as you would see, this is how research notebooks would look like. They don't look very neat and tidy the way that you people write, or I used to do at least as a college student, very neatly written, with usage of colored pens and pencils to highlight different regions of the notebook, and very attractive looking kind of notebooks. This doesn't happen in research at all, because we will be putting down things as and when we observe. And it is most important sometimes these little notes that, for example, you see that some circling has been done or a box has been put. Those notes are extremely important, which may appear very silly at the time of taking down a note, but at the same time later they could be actually providing the most important parameter to analyze what is happening to the system. So lab notebooks don't look all that tidy that you are familiar with in a practical class notebooks that probably one prepares. So that's one aspect that I wanted to show. So the master himself was putting down numbers and also his abbreviation for the elements, and trying to find the association of whether it is whether it is possible to look at the bigger picture, to look at a situation wherein there is some correlation between the way the chemical elements organize themselves. And so therefore it would be much easier to understand the system or the system of elements and get their properties to be under our control. Otherwise it would be a potpourri of hundreds of elements and one doesn't know how things behave. So that was his thinking, and that's how he started making notes, and finally came about giving us the periodic table. On the right, you see a very neatly laid modern day periodic table with lots of information. If you go to the web, you will see that they are all very interactive periodic tables that are available. So if you click on any of the elements of interest, you will get a whole lot of information that has been acquired over the years for each of the elements, and the properties are very well classified, and so therefore it would be much easier now to understand how elements behave once their place in the periodic table has been identified. That was not so, of course, when Mendeleev started his work. So these two things tell us that how research progresses from the left of the table, from the left table to the right table. Lots of people, including Mendeleev, have worked in order to achieve that kind of a transformation from a lab notebook to the modern periodic table. But spectroscopy has played a very important role in order to achieve, in order to put the periodic table on a firm footing. It has contributed significantly. And today's talk is to highlight the importance of spectroscopic contributions to make the periodic table the way it is today. So, as I said earlier, you would probably have wondered why I brought the first part of the title, Lead Kindly Light, and then I said spectroscopy and the periodic table. So, okay, if the host permit, actually questions can be asked anytime. I don't mind that kind of a thing. Dr. Umesh, you may please ensure that any questions asked can be passed on to me, even on the box. Dr. Umesh? I don't know. Hello? Hello? Hmm. Sorry for that interruption. So let me continue. So, Lead Kindly Light, I took that part actually from a well known poem from the 19th century poet John Newman. Um in fact, this poem may not be, which it actually reads like Lead Kindly Light amid the encircling gloom, lead thou me on kind of thing. It will go on. A lot of us may not be familiar with this poem, but at least some of us, people of my generation certainly, and even younger generation may be more familiar with the Kannada version of this, or a version that was translated to Kannada by that erudite professor, Professor B.M. Shri. And this is a well-known Kannada piece now, Karunalu Ba Bedake. We may be familiar with that. In fact, this celebrates the importance of light, or as the presentation goes, you will see that it is not just a light, but it is rather the wavelength discrimination of light, or spectroscopy, that is most important as far as the periodic table is concerned. So that's why I thought that actually this connection between lead kindly light, so the light actually led the enlightenment of people to arrive at the final version of the periodic table. So succinctly, this poem describes what has happened during the evolution of the periodic table. So I thought that's why I'll choose this kind of a title. So having explained that, let me put in very brief terms what I'm going to talk about today. I'm going to give a very brief introduction, maybe a slide or two of the presentation, and then I will go on talking about uh, in the mode of telling stories. Couple of stories I'm going to tell. And so the first story is about the gas burner and the chemical elements. And in fact, this brings in what could be called as network analysis today, what's being called as network analysis today. And for the person who came up with this network analysis, this entire thing was just a child's play. So I'm going to bring in the connection between this person and the periodic table. And then the second story is about the lazy but the noble lots. And there is also an NOBEL here, both NOBLE and NOBEL. I guess that I'm certain that you know the difference between the two. There is an Indian connection to the periodic table in this particular aspect. So I'm going to bring about that aspect of the story. And then the next story is about how an young man laid the basis for the modern periodic table, which the master Mendeleev himself had not approved it in the beginning, and then how his loss has been to science. This I can go on like this with several stories, but probably I'll stop at some point and then talk about some postscripts, etc. So, in order to appreciate the periodic table and the chemical elements, what we need to probably also look at the global perspective. When I mean globe, I'm not talking about the Earth itself, but the entire cosmos of how chemical elements have distributed themselves, or their abundance itself could be significantly dependent on the kind of roles that they have to play in the grand picture. So, if you consider the universe, for example, hydrogen and helium are the most abundant elements, forming about 98% of the total content of the universe itself. Oxygen, it's pity, it's only about 1%. Oxygen is only about 1.4%, but the rest of the elements, all the other elements that we know about today that could be present in nature, apart from the man-made ones, the entire thing falls under 1% of the total content. But now, from the universe, you zoom in and come down to Earth, let's say, and then the parameters change, the scenario changes. Oxygen now is the major occupant. It takes about 46% of the entire content of Earth's crust. Silicon is the second player with 28%, and the rest of them actually playing smaller roles. And each of these could be an important element despite their smaller content. And one example of that is, let's pick up this magnesium as a possible example. And for magnesium, what we see is about 2% of the total content. But despite that, its presence is extremely important as far as human life is concerned. And again, on the right side, I have put another P chart wherein different elements now play different roles, and their content also changes significantly. But coming back to the magnesium aspect of it, the dietary restrictions tell you that maximum intake of magnesium for any healthy person per day is only about 400 milligrams. So at any given point in one's lifetime, the maximum quantity of magnesium that could be present in a human body, let's consider, for example, a person who weighs about 60 to 70 kilograms, and the maximum magnesium content in such a person is a paltry 25 grams. Such a small quantity, but that small tiny bit of magnesium is an important component, and if it is deficient, there can be serious problem. I'll come to that in a moment of the kind of problems that could be there. But the magnesium plays an important role because it controls about 300 biochemical reactions and a host of other functions, including keeping us a healthy, steady heartbeat. And so, therefore, despite the presence of such tiny trace amounts of different elements, the body functions seriously depend on their content. So this is how actually we try to associate a variety of topics. I'm talking about biology, physiology, in fact, and I'm talking about periodic table. So the importance of the periodic table doesn't get limited to just chemistry, but can affect a whole variety of topics today. In fact, my last postscript is about how it can affect even completely removed topics completely removed from science could also be seriously affected by the periodic table. I'll come to that at the end, in fact. So uh, let's start with the first story where we are talking about the gas burner and how the periodic table is affected by the presence of the gas burner. So before that, how spectroscopy actually comes into play is something that we can look at. Maybe I'll skip these slides. I'm already seeing that I'm running a little behind schedule of what I had planned. So I'll go to this slide, and what we see here are eye-pleasing things, and Deepavali is just about 2 months or 1.5 months later. So therefore, this is something that we are all going to enjoy during those times, at least, if not an India-Pakistan match. So the colored fireworks, this was derived and developed primarily in China around 14th century. They have records to show that they could actually design fireworks of different colors. They could dictate what kind of colors the firework should exhibit. And so therefore their recipes were very clear to them. The low nitrate gunpowder and a mix of other kinds of elements, not only for entertainment purposes, not only for fancy things like the fireworks that we see on celebrations, but also as a military signal smoke. So Chinese had already developed this knowledge of the kind of elements that need to be incorporated in low nitrate gunpowder in order to get different kinds of colors. But of course, today it's a well-known piece of science that we exactly know which is the component that we need to have, which is the either the alkaline or alkaline earth material that we need to have in order to get precisely the color that we want: red, orange, yellow, green, etc. Strontium salts, calcium salts, different kinds of things, and we know precisely the kind of color that we can achieve when the firework takes place. So this kind of a thing, this kind of a knowledge preceded the kind of understanding that came from the gas burner. And so why am I mentioning this gas burner? This is something that a picture that is very familiar to all of you, especially once you have crossed perhaps the 10th standard, and when you enter the chemistry lab, you this is a very familiar scenario that you see the gas burner. Okay, so in fact the teacher tells you that this is called as the Bunsen burner. So Bunsen burner is such a common sight, we take it for granted today, but not so before this man. Actually, name is Robert Bunsen. 1855 is when he came up with this Bunsen burner. So way back in 19th century, people were not very clear about certain aspects of the burner, of how the flame can be controlled. And the big contribution from this man is not only about the burner, but there are other topics that probably I will mention tangentially. So Bunsen, the goal that he was given when he joined the University of Heidelberg as a chemistry faculty was to study the colors of light emitted when different elements were heated. Uh, the observation of Bunsen and other scientists at that time was, whichever flame that you were employing, it always burns yellow with a very sooty flame because of the presence of carbon. So his observation was that this kind of a sooty flame creates a problem because the incandescence from carbon atom masks any other color that a particular element may be generating when heated to much higher temperatures. So obviously the need for the burn that he had were a device that would produce a flame with very little soot. Soot is nothing but carbon, with the aim of maximizing the temperature and minimizing the luminosity that was coming from the burning of carbon. So that was the kind of goal that he had when he started his chemistry research. So this is something that we are familiar with today. Perhaps you know the details of what the Bunsen burner is. Yeah, sorry, I don't know. Uh, just a minute. Yeah. Yeah. So this is what describes a Bunsen burner. I won't go into the details except to say that you see a collar here and an air hole and a gas jet. Of course, we take all these things for granted today, but those days, before Bunsen actually put his thoughts together and came up with this Bunsen burner, this part was missing. The air hole and the gas jet mixing point of it, which could be controlled, was missing those days. So therefore, he came up with this idea that he and an engineer in the University of Heidelberg, they came up with this idea that the amount of oxygen that should be supplied to the flame should be very well controlled in order to dictate the kind of flame that you should get. And today it's child's play to get any of these flames, 1, 2, 3, 4, depending on the amount of oxygen that you supply to the flame, you will get a variety of colors. And of course, blue is what you want in most of these kinds of cases because it achieves the highest temperature possible. And also, you have almost a colorless, very high temperature region just above it, where you keep the element and get the characteristic color that comes out of the element, and therefore you should be able to identify the element just because of the kind of color that it emits when heated to high temperature. So Bunsen's contribution is an important component today of what is called a flame test to identify the elements. And this is used today, even today, flame test indicators are very popular, even in forensic laboratories, wherein it is used for the kind of need that a forensic scientist has to work with. So other contributions of Bunsen should not be ignored. He came up with tests to identify cesium and rubidium elements, which became much more important much later than his period. And the kind of scientific work that they had to do, which is true today also, a scientist, first of all, must have a lot of patience. Without patience, you can't be doing experimental research. So just to give a flair for that kind of a statement, in order to isolate, in order to get about 17 grams of cesium, he had to distill 40 tons of water. 40 tons, 40,000 liters of water had to be distilled in order to get about 17 grams of cesium. So that's the kind of patience one should have in order to achieve the kind of results Bunsen or anyone who has got acclaims for that kind of an achievement should be possessing. So, but Bunsen's was a simple observation that from the frame test that you put an element and you get a characteristic color coming out of that. But to put this observation on a firmer footing, to get good correlation between the elements and the kind of color that one gets, you had to have a person called Gustav Robert Kirchhoff. And I'm certain that again, this is another name that all of you would have heard in the physics class when the teacher would be teaching you something about the network analysis, circuit network analysis. Whenever they teach you that, they would be talking about Kirchhoff analysis. And so you can't escape that very easily. But this Kirchhoff made this network analysis not as a researcher, but just as a student. He was asked to give a seminar, and his idea was not to repeat something that was already well known. So he came up with this novel idea of how to analyze electrical circuits using the kind of analysis that he came up with, which makes network analysis extremely stable and also extremely understandable even today. And even today, electrical and electronics engineers employ Kirchhoff's rules in order to understand how circuit elements behave. So we should be saluting this person not only for this contribution, but to a whole lot of other things that he did and has contributed. At least three of them I'm mentioning here. The first I've already mentioned, circuit laws. The second thing is about thermochemistry. Where is physics and where is thermochemistry? And look at the kind of contributions that this man has done. And the last of the one is most important for us today, his three laws of spectroscopy. So with this kind of a thing, Kirchhoff came up with a spectroscope which made them identify a whole lot of elements in subjecting them to to high temperature flames, and looking at the color, the spectroscope could identify the kind of element that is present in the kind of material that was subjected to the high temperature test. So let us quickly look at the three laws of spectroscopy of Kirchhoff. The first one says that a luminous solid or a liquid or a dense gas produces a continuous spectrum. And I have indicated here what I mean by a continuous spectrum in the visible region, in exhibiting entire spectrum of Vibgyor, going continuously from the red to the blue region without any break. So there is a continuous transformation in the wavelength going from the red to the blue. The second law states that if there is a low density gas, but it is hot, then it will produce a series of bright lines characteristic of the chemical content. And now, instead of having a continuous spectrum, what you have is now a series of lines which are characteristic of that particular chemical content. And now what you have is an emission spectrum which is a line spectrum, unlike the continuous spectrum that you saw with the first law. So the third law is now talking about not a hot low density gas, not a hot high density gas as was the first case, but rather a low density gas that is cool. But now this absorbs certain wavelengths from a continuous spectrum, leaving dark absorption lines. You see the absorption lines here. The dark lines are the absorption lines against the continuous background. And these the position of these absorption lines are characteristic of the chemical content which is producing these lines. So these three laws can be quickly applied to understand a variety of situations. And here we are looking at one astronomy situation. It is not an astronomical situation as I put it here, but rather an astronomy situation and an astrophysics kind of situation. So let's carry the message from the previous slides. The type of spectrum depends on the temperature of the thin gas relative to the background temperature. So there is an object which is giving which is at a higher temperature, let's say with respect to the background temperature, with respect to the background. And so then we are going to analyze to see what kind of spectrum that it is going to exhibit. So consider a cooler gas that is surrounding a hot star. So the hot star, for example, here could be the very familiar, the sun. So one observes a continuous spectrum, but they are interspersed by dark lines. And these dark lines are against the continuous background was already seen by about 50 years ago by another scientist by name Fraunhofer. And in fact, they carry his name called Fraunhofer lines. So the hot gas used actually dictates the kind of the dark lines that are present here. So using this kind of analogy and then translating to this lab to see which element actually provides these the position of these dark lines and observing them in the lab, Kirchhoff could actually establish the kind of correlation between the spectrum that is observed in the laboratory with a known element, and then extrapolating that information to the spectrum that is observed from celestial objects, and then conclude on the kind of chemical content in those kinds of celestial objects. I've given some details here, and without going into much of the description, what I want to conclude here is Kirchhoff could show that using this kind of an analysis, Kirchhoff could show that the sun contains sodium. So this is a beautiful demonstration sitting here on earth and then thinking about and then demonstrating what an object which lies crores of miles away from us, of what the chemical content of that particular object. A beautiful demonstration. A simple lab level apparatus can help you in understanding what actually exists in a far off place like the sun. In fact, he also showed that the sun contains hydrogen as well. So, in fact, this makes me also give this kind of a statement. In fact, both Bunsen and Kirchhoff, using this kind of analysis, he helped astronomers to find new jobs, because now they could now conduct their tests on a variety, on a whole lot of celestial objects that are there in outer space, and then analyze what are the chemical contents and how the birth or the life of a star could be analyzed depending on its chemical content, etc. So it became a big business for the astronomer using this kind of a spectroscopic analysis that these two people could come up with. So that's for you spectroscopy and the first entry of that into getting into the periodic table or analyzing how chemical elements behave. So you can work backwards, and then given a particular chemical element, you can say what should be happening to its spectroscopic aspect. So this correlation is very well established, and this is also useful in putting them on the periodic table in the proper perspective. So I'll go to the next story then. The lazy but the noble lords. I don't know how many of you don't follow Kannada. I'm sorry for them. But in Kannada, there is a proverb. I don't know whether there is a proper translation in English. I will try to do that. At least the Kannada proverb is Summane iddavanannu brahmanu gellalara. Or if I want to do a very loose translation, I could say that if one doesn't react, that person cannot be won over, which means that you can't claim victory over a person who doesn't react to a situation at all. So this kind of a situation can be applied to this story that I'm talking about in the next few slides. So it almost unfolded like a drama. And so therefore I'm putting it like a scene 1, scene 2 kind of thing that you would see probably in a Shakespearean play. And the two main characters of this play happen to be Sir William Ramsay and uh, Lord Raleigh. And of course, the big aspect of that, at least keeping today's announcement by the Nobel Committee, is that again a Nobel Prize was associated uh, with this work, and that was in 1904, and the very first Nobel Prize to be won by a Britisher. That kind of an importance is built into the story that I'm talking about. Uh, in Mendeleev's time, which is about the same period that I'm talking about, the identification of an element was very tough. A practical way of doing was to look at the chemical reactivity of the suspected element. So people used to employ all kinds of reactions to a chemical element in order to understand, in order to identify which element it could be. People were even tasting elements. Of course, there were some disastrous results as well. People, when it could be fatal if you are trying to lick an element which could be poisonous. Mercury being a very good example. So therefore, but let's not dwell on that. So that's why it was surprising for anyone to imagine anybody's plight of trying to identify an element which does not react at all in the true sense of the word. So, two people get the credit for this. I have already named them, Ramsay and Raleigh. Uh, it all started with a very innocuous note, very simple note. The date was 19th April 1984. Ramsay would be attending a lecture at the Royal Society by Raleigh is the person on the right, and Ramsay is on the one on the left. And Ramsay would be attending this lecture by Raleigh. And the title is a very simple one, on the composition of the air. So, while describing the work that he has done, John William Strutt is better known as Lord Raleigh. He would be describing something that he had just then published in Nature, a very celebrated journal, scientific journal, even today. And then finally puts up a question to the audience, saying that I'm much puzzled by some recent results as to the density of nitrogen. He's talking about the composition of the air. So, density of nitrogen, and she'll be obliged if any of your chemical readers, he's specifically talking about chemists, chemical readers, if they can offer a suggestion as to the cause of what has happened in my experiments. So, the problem that he's talking about is that he finds a substantial discrepancy between the density of nitrogen made by chemical synthesis in the laboratory and the nitrogen that is isolated from the air by removal of other known components. This is how actually people identify the different components of air, by taking out all the known ones and then analyzing the remaining ones. So the difference that Raleigh was talking about was extremely small, about 0.1% or 1 part in 1,000. A careless experimenter probably would have brushed it under the carpet, saying that probably there is some error in measurement. But Raleigh was a very careful experimenter. So he was certain that all the errors that he could be having in the experiment cannot explain this discrepancy of 0.1%. And so he was confident in saying that they lie entirely outside the errors of the experiment. So therefore, he gives a call asking people to help him to understand the discrepancy between the two. In fact, he says that, is the contamination by a lighter gas in the synthesized one responsible for this? Ramsay, who would be sitting quite attentive to the talk, quips, makes a comment saying that, tongue-in-cheek kind of comment, says that, Why not the opposite? It could be a heavier component in the atmosphere. In fact, he was not just making an off the cuff kind of comment just because he wanted to make a comment, but he was guided by what he had just some months ago had read about the work almost a century ago by Henry Cavendish, wherein he had done experiment about fictitious air, and then trying to find correlation between Rayleigh's observation and Cavendish's notes. Ramsay thinks that whatever Rayleigh is observing is because could be because of the opposite thing of a heavier gas in the atmospheric air. So after the talk, the two discuss this problem further and come up with a collaborative program. This is how actually even today scientific collaborations get established, that two people have very similar kind of problem seeking intentions. They want to work on a similar kind of problem, and they could be attacking the problem from different different angles, and so therefore they could forge a collaboration and work together. This was a very intense collaboration that took place between Rayleigh the physicist and Ramsay the chemist, and scene 2 unfolds in August 1894. That was April, the talk. August 1894. Already the experiments have yielded results. 4th August, look at the kind of chronology that I'm going to quote. 4th August 1894, Ramsay isolates the new gas and informs Rayleigh. He, of course, please remember, I'm talking about 19th century. When I say informs, this is by writing a letter. It is not that he sent an email or a WhatsApp kind of message to Rayleigh. That was not possible those days. So 2 days later, Rayleigh replies to Ramsay, I too have isolated the gas. He was also working on the problem. I too have isolated the gas, though in miserably small quantities. But probably when it comes to isolating chemicals, your physicists are no match to a chemist, a trained chemist. And so therefore you could excuse if Rayleigh says it's in miserably small quantities that he could isolate. But the fact that two people working in entirely two different laboratories but having different kinds of training in science could come up with a similar kind of answer establishes the reproducibility of the result, which is a very important aspect in any scientific research. Reproducibility by different people is the basis of science, without which nobody can give credence to the observations by any scientist. So it appears that they have found indeed a new element. Within a week, and with the help of spectroscopic evidences that they could forge from a third collaborator, on the 13th of August, 6th of August is when Rayleigh communicates to Ramsay to confirming that observation. 13th August, they announce to the Royal Society that they have found a new element. Argon is what they call it, and argon means the lazy element, or because it was not reacting with anything that was known, so therefore they called it the lazy element or the argon. In fact, this nomenclature is now gone. People call it as not even as inert elements, but rather as noble elements, noble gases. So this discovery got the two guys their Nobel Prize. But as it happens, and it should happen, I'm not discounting that aspect, but it happens to even good experimenters and even well established experiments. That's the reason I'm showing this cartoon. There are always people who doubt, there are skeptics who don't believe any discovery in the beginning stages. And no exceptions actually. You could be big, you could be small, you could be doubting a particular experimental observation, a particular scientific discovery. And I'm bringing in the master himself. Mendeleev himself didn't believe that argon could exist. because argon was an inert element, and Mendeleev's periodic table, at least at that time, depended entirely on the chemical reactivity of the element. So if a particular element doesn't react, it had no place in Mendeleev's periodic table. He just didn't believe that there could be such a chemical element which doesn't react with any other element. And in fact, they were, and all such people also joined the bandwagon of Mendeleev to say that in fact argon doesn't exist at all. But Raleigh actually left in frustration. He didn't want to continue on this research. He went on to something else. But Ramsay actually didn't give up. 5 more months of intense research and an incredible and a watertight kind of evidence coming from spectroscopy. And then Ramsay had beautiful evidences that this gas must exist. And he gives a talk at the Royal Society on 31st of Jan 1895, saying that the title was Argon, a new constituent of the atmosphere. So that was the kind of belief that Ramsay had got to say that they have established a new kind of element, looking at the spectroscopic evidence, which looks actually like this. I won't discuss the details of this kind of an evidence, but it's a very important aspect of how to get evidence for the presence of the noble elements. I've put it as other nobles. The title of this slide is Other Nobles. In fact, the next element, in the passing, I can say that Mendeleev actually didn't believe the existence of noble elements for another 7 years beyond 1895. One should remember that. Ramsay continued to work in this field and found the other noble elements. The first such is actually an alien element. And what do I mean by an alien element? Is because it was not first found on Earth, but in a celestial object. And so therefore, I'm calling it an alien element. And here is where there is an Indian connection. Just 1 second, I want to check with the host. I'm sorry, I don't know what's the duration. Is it a 1 hour talk or?
Sir, you can continue, sir, another 10-15 minutes.
15 minutes. Okay, you are gracious already. I may go a little beyond that. 20 perhaps would be a luxury time for me. I'm certain that I would be able to conclude before another 20 minutes.
Please, sir.
Kindly permit me to do so. So this person, the new player in the field, is not a chemist, is not a physicist, but actually an astronomer, a sky gazer. His name is Pierre Janssen, and he's a solar spectroscopist. And around that time, when he got interested in this problem, this was before these people had identified the element. 1868 is when he comes to India, to Guntur actually, which is not too far from Bangalore. 1868, he comes there for what? To observe the total solar eclipse. Why should he travel all the way across the continent to come to Guntur to do this observation? Because he wanted to reduce the noise and to see the spectrum of the sun, which can be reduced noise. And so therefore, during total solar eclipse, which was happening, which could be seen in these parts of the world that particular year, so therefore he traveled across the continent to come here. And then he found a spectrum and found a bright yellow line whose wavelength did not match with anything that was known to mankind at that time. He was going back to the way that Bunsen and Kirchhoff had established of the correlation between the element and the spectrum. So therefore, there was no match, and so therefore he was puzzled, and so he keeps it as a puzzle. So at the same time, another British astronomer, his name is Lockyer, but he sat tightly in his hometown and then did the same observation during that eclipse. He found the same kind of thing, that there is a bright yellow line which cannot be ascribed to any known element, but it was coming from the sun. So therefore, he gave the name helium, because Helios is the Greek name for sun. So it was seen in the sun, so therefore he called it helium. In fact, later the spectrum of the volcanic content was also found in the lava of Mount Vesuvius by a volcanologist, Pommery. And all these things actually were pieces of puzzle. And it so happens that Ramsay, who was already well known in this field, was sent a piece of a mineral by an American mineralogist and asked him to do some spectroscopic studies. So Ramsay does a detailed study of the spectroscopy. He knew how to now identify elements using spectroscopy. So therefore, he finds that in the volcano lava, in the mineral that was sent by the American, and in the spectrum that was seen by this astronomer, they all had a common pattern of the bright, what we call as the D3 line today, at 587.5 nanometer, is indeed because of this new noble element, or the new gas that he has found, called the helium. He went along with Lockyer to keep the name helium to this, and thus helium became a part of our human life. And of course, we are very familiar with helium today as the content of our birthday party balloons. It was put on a firm footing in science. But now you see, the credit of Ramsay, I should say that 1894 he finds argon, 1895 he establishes helium. In fact, one could have rested on the laurels of these two scientific achievements and had a very lazy time beyond that, even in science, but not with Ramsay. He works continuously at a very amazing pace, and look at what happens with his team. They discover neon, another noble element, in 1898, krypton the same month, June 1898, and then xenon in a few months later, 1898 September. So in a span of 4 months, this group comes up with so many new elements based on the beautiful evidence that they could build using spectroscopy. It's as if just because he wants to have some courtesy to the fellow researchers, this group left out radon, which is the last of the noble element in this periodic table, to some other researcher to identify and then come up with the establishment of another noble element called the radon. But look at the uphill task that these people had to face in order to identify these kinds of elements in the atmosphere. The content of each of these I have shown here. Argon is about just less than 1%. Helium is 5 parts per million. If you take 1 million air molecules, helium is only 5 molecules of that. Neon is 18 ppm. Krypton, 1 ppm. And look at the miserable quantity of xenon in the atmosphere, 0.09 ppm. Terribly, extremely abysmal quantities of these materials. And look at the additional problems. They become liquid or solid at extremely low temperatures. They are colorless, they are odorless, they are tasteless, and they are monoatomic as well. All this increased the kind of research difficulty that one had to have in order to bring in their establishment to put them on a firm footing. And here is where I want to digress a little bit and bring a second Indian connection to the entire science and the periodic table. Uh, this is about this person, Maurice William Travers. Maurice had worked on these noble elements when he was a student with Professor Ramsay. And the Tatas, who built scientific institutions, several scientific institutions across the country, were looking for a new director or the founding director for their new institution, which was coming up in Bangalore. And so therefore they would have written to Ramsay, asking him to recommend a person suitable to become the director of this new scientific institute. Without any hesitation, Ramsay recommends Travers's name, because he was such a meticulous researcher, a very systematic researcher. Ramsay thinks that he would be the ideal person to head the institute, which would be making a new beginning to start important scientific research in India. And that's how Travers becomes the director of the Indian Institute of Science, uh, um, and founded a beautiful institution, which is a scientific landmark even today, of the highest kind of scientific landmark that you can have for any scientific institution anywhere in the world. And that's how we have this premier institute. And obviously it is because of the nice foundation, scientific foundation, that Travers had laid, that this institution has grown to this kind of a phenomenal level today. So if you were to look at the periodic table as was prepared by Mendeleev and today's periodic table, both images that I showed in the beginning, you would find a significant difference. The parameter that Mendeleev and others who were working on the periodic table those times, the parameter that they employed is quite different from the parameter that is employed today to prepare the periodic table. So the arrangement of the periodic table as is done today relies upon an entirely different basis, entirely different parameter than was done by Mendeleev and others. And we are talking, the third story that I'm talking about is on this person, an young man who laid the basis for the modern periodic table. He's again a Britisher. His name is Henry Van Geoffrey Moseley. There's the picture of the person. And when Moseley entered the scientific field, X-rays and their interaction with matter had become a very hot topic. Low-wave diffraction pattern of inorganic compounds, diffraction by crystals, the so-called Bragg's law, which laid the basis for crystallography. A whole lot of things were getting developed when he entered the lab of Rutherford. So, but rather than working on the problems that his Professor Rutherford, was asking him to do, Moseley's thinking scientific thoughts were always on, are there better alternatives to atomic weight, which Mendeleev used as the basis to prepare the periodic table? Are there better kind of bases that can be employed in order to come up with the periodic table? A parallel development that was taking place in Rutherford's lab itself was that they had shown, Barkla and Rutherford had shown, that nuclear charge is approximately half the atomic weight of the element. And please remember, at that time, the atomic weight was a basis. So another person, again entirely removed from science, a Dutch economist, but an amateur scientist. His name is Brook. He proposed that a new fundamental particle, alphon, which has a charge of +1 and a mass of 2 units, must be the basis for the periodic table and not the atomic weight. And he wanted it to be arranged on the basis of alphons, in which each element differed from the following by a +1 charge. In fact, he thought that it can solve a variety of problems that Mendeleev's periodic table had. I won't go into the detail here, but probably we'll touch upon later. So Moseley was less interested in the experiments that Rutherford had assigned. Even he writes to his mother saying that Professor is more interested in me tinkering his automobile than carry out the scientific experiments that I'm interested in. But anyway, at the time, a boon occurs to Mosley. Niels Bohr, who would be working on the atomic model then and had already become quite famous on that, would be visiting Rutherford. And then he coaxes Mosley to do X-ray dispersion, and the degree of scattering of X-rays could be proportional to the atomic charge rather than the atomic weight. Is a prediction that he was working on. Niels Bohr would be working on. So he coaxes this young man, if you want to do something different, do you want to take this up as a challenge and do some experiments that could prove or disprove my kind of thoughts? Mosley readily agrees. And look at the audacity of this young person. Niels Bohr was already an established researcher, but Mosley says, we shall see. Let's see what happens in the experiments. He doesn't readily agree with Niels Bohr. So he brings up this new topic of X-ray spectroscopy, and he establishes the new kind of apparatus that was required. I won't get into the details, but I would urge you to go and read details of how Mosley came up with a very robust way of doing X-ray spectroscopy, and using a series of elements that had to be tested in a very short duration of time. He could come up with a beautiful evidence of how X-ray spectroscopy can be employed to understand the nature of the chemical elements. And the most important contribution from him is that the frequency or the wavelength is what or something that's proportional to the wavelength. The square root of the frequency of the X-rays reflected from an element, it is proportional to Z minus 1, where the Z is the charge on the nucleus of the atoms of the element. So he becomes quite courageous with this kind of an establishment. I have shown a scatter plot here of a number of elements that follow this kind of a rule of his, that they have a direct connection, that there is a direct connection between the frequency of the X-rays reflected and this value of the Z, or the charge in the nucleus of the atoms of the element. So he establishes that atomic number is a measurable parameter, and gives it a physical meaning, saying that the number of protons in the nucleus is nothing but his Z. And so therefore he should be able to use this as a parameter to put the element in its proper place in the periodic table. So therefore, the modern periodic table is born and given birth to by Mosley. In fact, this X-ray spectroscopy is popular even today by as far as the astronomers are concerned. And for example, even such observations as a supernova remnant, for example, people identify using X-ray spectroscopy of even such distant objects like celestial objects or galaxies or supernovae. They're all identified using the X-ray spectroscopy that Mosley came up with. I have put the title of this in a very sober mode. 1915. Please remember, Mosley is a very young man. 1915, tragedy strikes. Mosley dies at an young age of 27. And how did he die? It was the time of the World War. And there, being a nationalist, being a patriot, he says he should be with the army that is fighting the enemy. So he enlists himself to be with the army, and he's posted to Gallipoli, a war front in Italy. And there he takes a bullet in his head and dies at a very young age of 27. His loss is not only to his family, to the country, but it is to the entire scientific community, that at such an young age, this man was able to give such a beautiful contribution. Had he lived on, probably science would have become much richer, providing us far better visions of his to come through. Would have been something that we would have all liked. But that's how things happen in life. I can go on like this with so many stories. There is a beautiful book, if you are interested, for Science, King and Country, The Life and Legacy of Henry Moseley. As an inspirational book, I would urge you to read this. It's a beautiful book. So I can go on like this, but probably I should stop. I've already exceeded 12 minutes, and probably before they cut me off from this online link, let me draw the postscript. Today, the energy dispersive X-ray fluorescence is a very important component, especially for both pharmaceutical industry as well as people, practitioners of nanoscience. Without, in fact, nanoscience people employ this, what they call as the DAX, very effectively in order to identify the kind of elements which could be present in the nano structures that they develop. It's a very important parameter that they employ. And in one note, I want to say XRF as well as EDAX are inseparable parts of today's frontline research in material science. And so therefore, in fact, I didn't go to the aspect of man-made elements. People have been making elements in the laboratory. So if you see the periodic table, there are a host of elements that are not put in the main part of the table, but rather moved out separately and put in two separate rows that are present in the bottom portion of the periodic table. And the bottommost part of it is coming from the man-made elements. And till now, elements with atomic number up to about 118 have been identified through these kinds of research. It's a big field itself of coming up with new elements. But why I brought this name of Feynman is because of the number that I have put there, 137. In fact, long ago, Feynman predicted that the maximum number of elements you can have is 137, or rather, the element with the maximum number of atomic number one can have is 137. And in fact, he establishes this kind of, he gives a beautiful proof of what happens to the velocity of the electron with those kinds of atomic numbers. And so therefore, there is a physical limit that comes from universal constants that puts a limit to the kind of elements that you can have. So even if I can come up with something like, let's say somebody comes up with an element which could be like 138, that probably would have a name like imposium or an imaginarium or an unobtainium kind of elements. In this postscript, I also want to bring in another aspect of human life and elements. Till now, what I talked about has direct connection with science and periodic table. But now what I'm talking about, I think I mentioned sometime in the beginning itself, that periodic table or the chemical elements have gone beyond science in today's modern world. Economics and politics are playing very big role as far as chemical elements are concerned today. So I'll give you one example of that. I have put three circles, or I have put three enclosures here for what are referred to as rare earth elements. And rare earth elements are making a big story today, making big headlines today as far as economics is concerned. And to summarize that kind of an importance of these elements, I want to quote that maverick politician of China, Deng Xiaoping, who some time ago said, nature has given petroleum to the Middle East. It has given rare earth elements to China. Very profound, very powerful kind of statement that tells you the importance of rare earth elements in today's economics. In fact, China is playing a big geopolitical, geo-economical kind of role as far as rare earth elements are concerned. About 37 to 50% of the world's availability of rare earth elements are concentrated in China. And each of these elements is an extremely important component in today's technological world. One simple example I want to give is that of indium, which is used to prepare indium tin oxide, an electrically conducting but transparent substrate that it can provide on glass, is an essential and a non-substitutable component today of all electronic gadgets which have a display element today, including the mobile phones or the laptop screens or the televisions that we have today. They all employ indium tin oxide as a component, and so therefore indium is already treated as a very precious and an element that needs to be, or its abundance need to be protected kind of element, already an endangered element is what. So therefore this kind of a scenario is something that probably you people can also think about, even if you are not getting into the science stream, even if you are going to become an economist or become a statesman of a country. Probably you should be thinking about rare earth elements as well to bring into the politics or the economics of the country. So I won't go into the details of those kinds of topics today. The last of the things is something that extremely sober note. All human achievements I talked about today, but we should always keep in the back of our minds as philosophers in life that nature has already done every single thing perhaps that mankind boasts of achieving. Nature has already done that. And with that, I want to close today's thing. And here is a little video about what are called northern lights. Let me run the video and then add my own one or two sentence commentary on that. I hope that you will be able to see the video as well as hear the audio. If you don't, you stop me, then we will see how the audio can be made audible. Oh, sorry. What happened? The northern lights seen above the magnetic pole of the northern hemisphere are actually the result of collisions between the gaseous particles in the Earth's atmosphere with charged particles released from the sun's atmosphere. Variations in color are due to the type of gas particles that are colliding. The most common auroral color, a pale yellowish green, is produced by oxygen molecules located about 60 miles above the Earth, where all red auroras are produced by high altitude oxygen lights of cooled mines. Nitrogen produces blue purplish red aurora. Yeah. Was it audible?
Yes, sir. Yes, sir. It's audible.
Okay, good. So I want to close here saying that what I wanted to show was that this beautiful display happens quite often in the two poles. In the northern pole, it is called northern light or aurora borealis, and in the southern hemisphere, it is known as the aurora australis. Aurora borealis is a more easily approachable region. So therefore, if at all any of you happen to go to the poles, you may be having an opportunity to see this spectacular display happening only because of the spectroscopy and the nature of the element or the correlation between them. So this is why I wanted to end with this note saying that spectroscopy has been and will ever play an important role as far as the periodic table and the nature of the chemical elements that we have around to play. Thank you very much for listening to this talk.
Thank you very much, sir. It's a wonderful and energetic presentation. Sir, any specific timeline or any specific season this spectroscopy happens in that zone?
Sorry?
When is the best time to visit that place, sir?
Actually, announcements are made, and you can keep a watch on the sites that report to Northern Lights, and especially when the solar flares are very active, these become more appreciable.
Thank you, sir. Thank you very much once again. Now there are 2, 3 questions we would like to take from the audience.
Yes, please.
Uh, why are some modern periodic exceptions? Why are come or I request Shivra Sutha to reframe the question. Meanwhile, you can take other question.
Yeah.
Sir, what is an atomic radius and what are its periodic trends?
What is what?
What is an atomic radius and how? What are its periodic trends?
I didn't want to get into these kinds of statistics kind of thing, which can be obtained anytime, anywhere from the web or textbooks. I didn't want to
Okay,
go
sir.
into that kind of a detail today. But
Okay.
these are very well established today. So therefore, I would urge you to actually go to standard textbooks and read about them rather than me supplying answers.
Thank you, sir. Thank you, sir. And one more thing, it's a similar kind of a question. What is the most interesting thing on the periodic table?
Ha!
That is,
I don't think you should be asking
yes, sir.
a
Yes, sir.
singular kind of point. It depends
Yes,
on
sir.
your outlook.
There are
I
many
gave
things.
one example. See, there are people who are very attracted by gold. Okay,
Yes, sir.
uh,
So it's for Indian context,
or
79 is the
probably
only
half the
interesting
population of the world
organism.
is attracted by gold.
Yes, sir.
Some people may be attracted because of its luster or its ornamental value. Some people who may be interested in it as a tool for investment and appreciation in financial terms. Some people, like for example chemists, who may be quite interested because of its inertness, and so therefore that can be employed for a variety of chemical reactions. Some people again in the scientific world may be interested because you can prepare nanoparticles of gold in far much easier ways than creating nanostructures of other elements. So therefore, it depends on the kind of outlook that you have. So if I take one single element such as gold, I can come up with a very different angles for which I should be interested in the periodic table. So I would not ask this question of which is the single most important element that is there in the periodic table. I would not, because I think earlier on I gave one P chart wherein I said that depending on the scale that you are employing, whether you are looking at the universe as a total, or the earth's crust, or the human body, the kind of abundance is quite different because it has different functionalities. For the universe, it is the energy which is most important to sustain the universe. So therefore both hydrogen and helium are in abundance. Whereas for the human body, the creation of energy is through oxygen. And so therefore the abundance again changes because of that. So it depends on your perspective on what you are looking at in order to identify which is the most important element, which is the single most parameter of the periodic table. But if your question was about as far as the arrangement of the periodic table, which is the most important element, which is the most important parameter, I think I've already answered that towards in the last story, that it is the atomic number. And in fact, I didn't go to something called pair reversals. Mendeleev had a serious problem. He could not answer that. Take the pair of cobalt and nickel. If you consider atomic weight to be the basis for the periodic table, their positions are reverse of what you find in the modern periodic table. And Mendeleev could not answer this because the atomic weight doesn't get positioned that way, whereas property wise cobalt and nickel behave the opposite of their positions in the Mendeleev's table. So whereas when you consider the atomic number to be the basis, everything falls into place, and cobalt nickel also find their proper places. So therefore it depends on what your outlook is when you are looking at the periodic table. Or to put it in a different kind of language, anyone going to a periodic table seeking any kind of a boon will get it granted. So that's what I can. It's more like a god kind of concept. You define your problem with respect to the periodic table, and probably the periodic table has the right answer for you.
Thank you, sir. How Ramsay extracted such small quantity of gas? This is one question from the audience.
I gave one example of cesium, for example, the distillation. This is a very painstaking kind of procedure when you are trying to extract extremely small quantities of the thing. So therefore, the apparatus has to be working very precisely, and the distillation has to be controlled extremely well. And so therefore, the isolation becomes a very important component, and that's where actually spectroscopy helped them. Whenever they were trying to extract elements, they kept continuously taking spectroscopic evidences for the material that was getting isolated, and that's how they could come up with without large quantities, and air is in abundance. So therefore, at least material wise, they didn't have to worry about the abundance aspect of it.
Thank you very much, sir. With this, today we would like to end today's session. Formally, we would like to thank you very much, sir, once again
It has been a
for this
pleasure.
wonderful and energetic. Most importantly, we can say that it's almost 1.5 hours. You have given us such a wonderful presentation, and the milestone of periodic table we can understand by your presentation. Thank you very much, sir. On behalf of KST and on behalf of all the teachers and my own behalf, hearty thank you, sir.
Thank you
And
very much.
also, I would like to thank all my colleagues, teaching technical team and non-technical team, and all the students and teachers who have joined with us in both the platforms, WebEx and YouTube channel. Thank you very much once again. Thank you, sir. Thank you.
I log off now.